Okay, here we go. Now it starts. Okay, I believe we are live. So hello everybody, and welcome to today's talk. On your screen you should see the holding slide for Lisa's talk and Lisa herself. So give us a wave, Lisa. That's brilliant. Okay, so the voice you can hear is not Lisa, of course, it's me, Sam Westwood. So I'm just going to do a bit of housekeeping before we begin. So as ever, the Rights Club have got a great series of talks coming up, so please check out our Twitter, and we're also migrating to Mastodon. We have an account and we're doing a whole announcement about that in a short while. We have another talk this week which is on the 25th, which is about crowdsourcing research questions in science. So, and that's been hosted by our Rotterdam site. So please check out their Twitter handle and their website. Just type into Google Right Science Club Rotterdam. In terms of housekeeping today, so for all newcomers, you're very much welcome. For all regulars, I'm sure you know this already, but I'll repeat myself. So the interface that you're in now, the live events interface, is really good because you can pause, rewind and fast forward the lecture. And there's also auto subtitling as well, so you can read along as you watch. The recording, for those any latecomers, if you think you've missed it, will be made available via YouTube in the coming week or so. So check out our YouTube channel where you can find all of our past content as well. Okay, so that's the opening spiel. Now on to the main event and why you're here. So we're very happy to welcome Lisa Debruine to today's talk. So Lisa is somebody who we look up to in the Rights Club and love the fantastic work that she's been doing through all these years. For those who don't know Lisa, which will be a shrinking minority, I assume, Lisa is a professor of psychology at the University of Glasgow School of Psychology and Neuroscience, and she's a founding member and current associate director of the Psych Science Accelerator, that large consortium that's making real landing lots of blows in psychological science now. She's also a member of the APA Open Science and Methodological Committee, and is, of course, a local network lead for the UK Reproducibility Network. And of course, she's also a member of the psyTeachR team for reproducible research educational resources. And you can find lots of her output on her website, which I'm going to put a link in the Q&A message board so you can see, and it can also direct you to the Q&A message board. So what we're going to ask you is, if you have any questions, please do put them in the Q&A, which you should be able to see on the right of your screen. There might be sort of two Q&A speech bubbles, and you can put your questions in there and I'll feed them to Lisa towards the end. That's enough from me, so I'm going to hand the keys over to you, Lisa, and thank you again for putting your time aside for this. And yes, the floor is yours.
All right, thank you very much. I'm really excited to be here at Riot Science Club today. Can't believe it's taken me so long to give a talk here. I'm going to be talking about code review today. Brief abstract just for the web version. But before we talk about code review, should probably talk about why do we code? Sort of as psychologists or as scientists, what's the purpose of coding? And the number one main reason I have to code, and the way I got into coding in our stats, is plots. So you can create amazing plots like this animated plot here that shows population distribution by age and gender from the mid-1900s to projections into the mid-2000s with just these 16 lines of code, which might look like gibber right now, but just a few hours with ggplot will make you understand this. You can reproduce it, you can modify it for a different color scheme, a different kind of data incredibly easily. I just want to plug Emily Nordman, who's giving a Riot Science Club talk pretty soon. Her paper, with the rest of, or many other people from the psyTeachR team, on data visualization using R for researchers who don't use R, is a really lovely way to start looking at the benefits of coding. Another thing that I am really excited about with why do we code? What can we do with coding that we can't do with SPSS or that we can't do with Excel is data simulation. So being able to simulate data allows you to do so many interesting things. So if you're doing a pre-registration or a registered report, you can simulate data with the effect that you're predicting and show exactly how you're going to analyze it. So there's absolutely no confusion about what your plan is. If you've ever tried to look on GPower for power analysis for a multi-level model or some other sort of analysis that's a bit esoteric, you'll realize how frustrating it is that there aren't analytic solutions to a lot of analyses. But if you can do data simulation, you can calculate power or sensitivity for literally any analysis you want to do on data. You can create reproducible examples so other people can see how your code works if your data are too big to share or too confidential to share. And also, I think data simulation allows you to enhance your understanding of statistical concepts. There are tons of things I didn't understand in stats. I did not understand mixed effects models at all until I started simulating data to see, like, where do the numbers go in for the data simulation, and then they come out in the analysis. Also, data simulation is good for creating demo data. I'll show you a little bit of a plug for an R package I've written called FO. You write code like this that just sets out what are your within and between subject factors, what are their levels, how many subjects in each level. You could have different numbers of subjects in each between subject level. The means and standard deviations for each of the cells, correlations for any within subject variables, and it will spit out some simulated data for you. Also has some plotting functions to let you have a look at what's going on with your plot, make default plots, custom plots, and it also has some newish multi-level functions. But again, all things you can do with code. But kind of even more importantly, I think, coding our data wrangling, so how we get from the raw data to the data we're going to analyze, which for a lot of us involves putting together data sets from in different files, doing some things like reverse coding, making subscale scores, and changing the shape of our data. All things that if you're doing in a kind of point and click in Excel can lead to errors. So Michelle Naughton and colleagues created a stat check, which I hope many of you are familiar with. But they looked at about 250,000 p-values that were reported in 8 major psych journals. And what stat check does is check to see if the test statistic, like an F value or a T value, and the degrees of freedom and the p-value are all correspond. Because, you know, if you're old enough, you know that we used to look up p-values from a table. Like, you would know your t-value and your degrees of freedom, then you go into this big book of tables and look up the p-value that corresponded to those two things. So they can check to see if they're consistent, and found that at least half, or about half the papers had at least one inconsistent p-value. And in 8 of the papers that had errors that could affect their conclusions. So from significant to non-significant or vice versa. Errors were more likely to be erroneously significant than not. Some people have interpreted that as a bit of fraud. I think more that it's, if you expected something to be significant and it wasn't, you might go back and double check, did you make an error? Whereas if something is significant, why look at it again? That these might be more biases in checking than actual fraud. But there are a lot of errors. And if you haven't shared your data and you haven't shared any code, it's pretty much impossible to figure out where the error came from. Was it misreporting of, was the p-value right, but the t-value was misreported, or the degrees of freedom misreported, or what? But even if people are sharing data, if they're not sharing the code that shows you how to analyze it, reproducibility can suffer. So Tom Harwick and colleagues looked at 35 articles published in Cognition that had the raw data, or the analyzed data included, and found that of those 35, only 11 could be reproduced independently from reading the paper, figuring out how the analyses were done, and doing the analyses on the data that was shared. When they contacted the authors of the original papers, 11 of them could help. They could reproduce all of the values in the paper. If the author said, oh, yeah, actually, we used this setting or we excluded these people and we didn't explain it in the paper well enough. So with a bit of additional information. 13 of them were not even reproducible by the original authors, which feels like, the lowest bar for reproducibility, that the same people with the same data and the same analyses should be able to get the same numbers at the end. But about a third of the time they couldn't. And Obles and colleagues looked at registered reports. So these are going to be some newer post-reproducibility crisis papers published 2014 to 2018. Of these registered reports, 36 had data and analysis code. They could only run 31 of them. There were some sorts of errors in the coding that made them not runnable, and we're going to talk about some of that later. And only 21 of those of the shared code reproduced all the main results. So again, we've got some irreproducibility here even with code, which means we need code review. Now, what is code review? It's the process of systematically checking over your code or somebody else's code after it's been written. Answer some of the questions here, but we're going to go into quite a bit more detail about how do we do code review, what are the sort of components of code review. But first, when I started getting interested in this, it was on the Twitter. I'm off the Twitter now, but you can find me at Mastodon. Debruine at tech.lgbt, and Mastodon is a much friendlier place, and there's lots of techie people. I think the RStats community is moving over there. But I started this, I was asking people on Twitter about code review. Do they do it? Are they interested in it? Do they know of resources for how to do it well? And a bunch of us came together and decided we wanted to do a code review project. So quite a lot of what I'm talking about today has come out of this code review project. And at the end of the talk, I'll show you the URL for the project and how you might get involved if you want to. But the first thing we did was send out a survey. We made a Google survey and asked people about their experiences with code review. If they don't do it, why don't they do it? And we found kind of three main areas of barriers to doing code review. So the first one's a technical barrier. People said they don't have the skill and they don't know of any resources. There's no guide for how do you do code review. Second type of barrier was incentive barriers. So people don't build time into project timelines for this. It's unusual to build it into a grant timeline for doing code review or getting money to hire code review done. It's not expected of people. The journals aren't asking you if you got your code reviewed or to confirm how the code was reviewed. Nobody expects it. But the more interesting one was we found there were lots of social barriers. So one was sort of expectations, just nobody expects it. Why would you do it? That's a bit weird. But a big one was fear of judgment. People who are user coders, they don't maybe have any training, formal training in coding, although lots of us don't have formal training in coding, but they don't do coding all day, every day. It's not a big part of their job. They just write code for analysis for their research, but their research focus is elsewhere. They're not very confident about the code that they write, and they're terrified that other people will judge them harshly based on their code, so they don't want to get anybody else to review it because they don't want people to see their code. I'm here to tell you that this is totally normal and it means you're growing. If you're not embarrassed by code you wrote 6 months ago, you're not progressing in that skill. And as an urge to the community, do not code shame other people. Everybody's at different places in their journey with coding, and we can be kind and constructive and help each other out while acknowledging that like lots of code needs improvement. Lots of my code needs improvement as well. But when we come together and talk about these things and try to do better, I think that's where we're going to make real scientific progress. All right, so before we talk more about like specifically what might you do in code review? So what are the goals of code review? And they're going to be different for different people depending on a few things. So one, depending on the stage in the research process. Is this review of code where the analyses are definitely set? You're just about ready to submit the paper? Or is it post manuscript review, code review? Or is it early in the project? It's also going to depend on the experience of the coder and the reviewer. If the coder's got a lot of experience, you might just be helping them with a quick check, make sure it runs, clean up any little things. Or if the coder's very inexperienced, there might be more work to do. And if the reviewer doesn't have much experience, there's certain things they might be able to do and certain things they might not be able to do. And also the amount of time you have available. So code review can be as simple as 5 minutes, download the script, see if it runs. If it runs, awesome. If it doesn't, let the person know and leave them to deal with it. Or I've spent, upwards of 12 hours doing code review for a manuscript I was reviewing, and I know that's excessive, but you can spend a lot of time doing code review if you're doing all of the things. So let's talk about those things. In this talk, we're going to focus on pre-submission code review by colleagues. I think that's the best place to kind of start doing code review, where if you've got a project you're working on with colleagues and one person has taken charge of writing the code, helping out in the project by doing code review for that person. Or if you've written the code, getting another one of your colleagues to do code review for you. We won't talk specifically about code review for reviewers of a manuscript, although a lot of the principles are the same. Although the one barrier with manuscripts is especially if they're blind review, you might not be able to ask questions. So there are points in the code review where you can just get stuck. That if you could talk to somebody and ask them a question, you could continue, but you can't ask them. So all you can do is write your question, stop the review. All right, so our first set of goals for code review is simple. Does it run? This requires very little expertise and time. As long as you know how to run scripts in the language that you've been asked to review, you can check and see if it runs. But this can result in one of the most substantial improvements in code. I think about half the time that I'm asked to review a manuscript for a journal that's already being submitted, and it has code, because I've ascribed to the Peer Reviewers Openness Initiative, and I only review papers that have open data and code. But about half the time when I do that, code doesn't run on the first pass. I've used absolute paths or some other things that we'll talk about that can stop code from being runnable. And if you get a colleague to just double check, if on their computer, they can download the data from the OSF or GitHub or wherever you're storing the data, or open the zip file that you might send to a journal. Can they open it up, download the data, click run, and does it run? And if it doesn't, you've got to fix some things. So ideally, you would get your colleague, or you would, if you were doing the code review, would access it from the same place that users would. So if you're sharing data and code for a preprint, are you putting it on the OSF? Then you would ask the code reviewer to download it from the OSF. Just give them that link, or however the reviewers would access it. Just make notes if you get errors. If you have the expertise to fix the errors, sometimes they're quite simple. Make a note about the fix and then try again and see, have you run into further errors? Because often once you fix errors at the beginning of a script, that can uncover later errors. The second kind of batch of goals, it takes a little bit more time, but not much more expertise, is checking for reproducibility. So this is whether the code gives you the same outputs as it gave the original coder. This means they need to send you the output so you can double check. So things like the analysis results as written in the manuscript, or plots or tables, or the HTML file output from a Quarto document or a Jupyter notebook, or an R Markdown document. So if you have those, and then checking that if you run the code, does it produce all those same things with all the same numbers? I can tell you that a very recent paper I've reviewed for a journal, when I ran the code, I didn't get the same numbers as were reported in the manuscript. And that is because they did not set a seed. And some of their analyses use bootstrap techniques that use randomization. And so if the randomization happens differently on two computers, you can get slightly different numbers in the results. They weren't big changes, but they were definite changes, and made me think. So setting a seed makes sure that two different computers will get the same reproducible random numbers. So the coder can make this whole thing easier for the reviewer by making it really clear what are the analysis results and the plots and the tables in their code and in the manuscript or any other like materials that they might send you. You can also let the coder know, if you're doing this kind of check, how straightforward is it to do the check. So if you're doing this as pre-submission, how much effort did you need to go through to match every number in the manuscript to a value in the code? Did their code output 10,000 lines of output that you had to search through manually for each number and was not well organized? Or did it have subheadings and very clear, like this creates figure 2, this one creates table 3, so that you could go match back and forth between the outputs and the code. All right, now requiring a bit more expertise and time is checking if the code is auditable and understandable. So is it well organized? Are you using things like literate programming, which we'll talk about later? And can you find, again, these corresponding parts of the output or the manuscript? Also checking if all of the parts of the process are available. So that it could be that you've gotten code that takes the raw data and turns it into the analyzed data, excludes some people, does some data processing, but nobody's giving you the raw data. All they've given you are the analyzed data and then further code. So it's difficult to tell where do you start, which bits are, like some of the scripts will run, some scripts won't run. So checking if everything is there that you need. And the final thing that you can look at or like the thing that requires the most expertise and the most time is checking if the code follows best practices. So you can spend a kind of infinite amount of time on this. So giving advice about general coding principles, things like whether or not the variable names make sense. In a recent review I did, someone used sort of numerically incrementing data frame and analysis names for their objects. So they would have data 1, data 2, data 3, analysis 1, analysis 2, analysis 3. And then at some point in the script, they became unlinked. So like data 4 went with analysis 5 and 6, and then data 5 went with analysis 7, 8, 9, and 10. And it became incredibly confusing. And I wasn't sure which of the data sets and other sub-objects were meant to correspond with each other and what they corresponded to in the paper. So giving advice about naming stuff. Also things like repeated code or values that are defined in multiple places. There's two principles, dry and spot, that we're going to talk about after this. Also another best practice about long processes. So if you're lucky, if you're working with smallish data sets, your scripts will run in a minute or two. I've had Bayesian mixed effects models that took 14 days to run. I wouldn't expect any code reviewer to do that for me. So you can tackle that sort of thing by saving the results of processes that take a long time or require a supercomputer to run. Save that, set the code somehow to not run, however that happens in the language that you're working in, and then load the saved data with a note about, here's the code that created this, here's why we're not running it right now, allowing the reviewers to check over the code sort of manually, but also skip the steps that take absolutely forever. And finally, are there sense checks or unit tests where appropriate to figure out, are you actually doing the things that you're meaning to do in like your data cleaning and data reshaping? Oh, that wasn't the final one? Okay, so our final one is a check that might require domain expertise. So again, most appropriate if you are somebody with a similar level of, or a higher level of coding experience than the person that you're checking. And also you might need to be in the same sort of disciplinary domain so that you can check to see if the code's actually doing what it was intended to do. Here, the coder can help you out by explaining well what did they intend to do, instead of making you infer what they intended to do by what code they wrote. You can check to see if what they intended to do was correct, if there are actual logical errors. So these sorts of things can happen. You can try to filter a data set to only look at women, but actually you filtered women out instead of filtering them in, and actually ended up with a different data set than what you had intended. But other things you might need this domain expertise, like if a questionnaire has reverse coded items that somebody forgot to reverse code. I want to be clear about what are not the goals of code check. So getting debugging help might be something that you need and you can ask colleagues to help with, but asking for a code check isn't debugging help. If you are doing a code check, you shouldn't be expected to help somebody fix errors in their code that they already know are there. Again, getting code help that they don't know how to do something or want help to make things more efficient. As a code reviewer, you might suggest ways to make the code better, but as a coder, you shouldn't ask somebody for code review with the intention of writing sloppy code because they'll just fix it for you. And additionally, statistical help. This is something that you can ask someone for, but it's not necessarily meant to be code review. So if someone says they've reviewed your code, it doesn't mean that they've checked your stats and made sure that they were the right stats to do for your study. That's a separate area of expertise. Okay, so now that we've kind of gone the overview of what's code review like, let's talk about some key concepts. There was a lot of jargon there that I use, like literate programming and dry and spot. So what are these key concepts that you might want to learn about in order to do code review better? First of all, we'll talk about what a review package should include. So if you're sending your code to a colleague to review, or you're going to bundle up your code to be reviewed at a journal, or you want to make it available associated with a preprint, you should include a README that describes the project, ideally specifying credit, who's been involved in the project, and licensing. What can people do with your code and your data? Being really explicit about this is better than just relying on implicit ideas in the discipline about what people can do with data that's posted on OSF or posted on GitHub. It should include any outputs that the reviewers should try to reproduce. So either a manuscript or the individual tables and plots, and things like results output. It should include all of the data used to create the outputs that need to be reproduced. If it's not possible for you to share those data, you can look into things like data simulation packages. Oh, I can't remember what the one is called, but there's an excellent one I think that Dan Quintana talks about a lot for simulating data where you can't share the actual raw data, but it can create some data sets that that you can demonstrate your analyses on. Make sure you send all of the code necessary to recreate the outputs. These sound like simple things, but these are all things that are often missing in data pack and review packages that I see. And a main script that runs any subscripts in the relevant order. Depending on what coding language you're using, you might have multiple subscripts, a bunch of .r files. And if it's not extremely clear what order they need to be run in, it can get really confusing for a code reviewer. So you can use a main script that's described in the README file that lists what order everything goes in, or literate programming ideas like notebooks. Right. Then send an organized project. So make sure that every single file that is used in the code, data files, the code files, any helper files, images you might be using in your literate programming are in a single directory, and that directory is the working directory of your project. So if you're using R Studio projects make this really easy. When you set up a project, if somebody else opens the project, that project directory becomes the working directory that they're working in, and then you can reference everything relative to your working directory. If you're using other languages where you might have to explicitly set the working directory, make sure that you explain this clearly in your code, do it once at the top of your code, explain it in your README, make sure that people know that this is a change they need to make to get it to work on their computer. Danielle Navarro has an outstanding slide set about project structure and how to structure these things. If you access these slides, that link will be clickable. And I'll give you the link to these slides again at the end. All right, file paths. Seems simple. It is where the majority of unrunnability comes from. So what are relative paths or absolute paths? A lot of people put absolute paths because this works fine in your computer. So if I'm reading a CSV file and it's, I don't have a PC, but in the C drive, in the documents folder, my R project, in the data folder, it's called docs.csv. This absolute path works fine for me, but if I give you my code, you probably don't have a directory called my R project inside the documents folder, right? You might have put this data somewhere else. You might have a Mac and not have a C drive. So what we want to do is use relative paths, where you start at the working directory, and then say that within the working directory, we look in the data directory and we look for docs.csv. Now, often if you have actually shared data docs.csv, a coder who's experienced enough is trying to run your code and there's errors everywhere and it can't find the data, can look through this and fix that. But the goal is to make sure that somebody else trying to run your code doesn't have to go through and edit a bunch of things in your code to make it work. Naming things. So I talked a little bit before about naming things, but naming both files in your project and code objects so people and computers can easily find them. So with files, often people need to make it more computer readable, and with in code, making it more people readable. So file and directory names should basically only contain letters, numbers, dashes, and underscores, with a full stop between file name and extension and no spaces. Now, depending on what operating system you're working with, putting in spaces and special characters and such might be absolutely fine on your computer. But on other operating systems, if other people are using them, they could have problems with these sorts of things. So this set of rules makes it pretty safe for nearly any operating system to be able to deal with your file names. Being consistent with capitalization, punctuation, and order. So I tend to not capitalize anything except for surnames. And then if you do things like always putting things in the same order. So Debruine underscore code dash review underscore the date. And this can be how I organize my talks. So who's the speaker underscore name of the talk underscore date. Then it'll be easier for me to go find files that I want to find later because I know they're going to be named that way. I can look in the alphabetical structure. using a pattern that alphabetizes in a sensible order. And for dates, there is only one correct way to write a date. Year-month, 2-digit month, dash 2-digit date. If you always do your dates this way, they will alphabetize in an actual order. If you do day, dash month, dash year, then the 1st of January, 1st of February, 1st of March, it's just all out of order, and also becomes really difficult to figure out, is this person using the American system? Are they using British system? So if you start with the year, I think everybody knows there is no such thing as year, day, month. So if you start with the year, 4 digits, everybody knows what's going to come next. Jenny Bryan has an outstanding resource called Naming Things that goes through all this sort of stuff in even more detail. Data documentation is another thing. When you're sharing data sets, making sure that they're understandable by people who aren't you. I fall down on this a lot. I feel like my column headers, they make sense, right? Probably they mainly make sense to you and your team and maybe people who are really involved in your research area, but they usually need a bit more explanation for other people. So when you're sharing data, if you could share also auxiliary files that give an overview of your data, so things like who are the authors of the data, if that's different than the whole project, date and location of data collection, sampling, inclusion criteria, what questionnaires or instruments you use to collect data, have there been any updates, and explicit licensing. How can other people use this data? Are there any restrictions? And then additionally, variable information. So the information for every column in a data set. What's the column name? What's the a longer description that gives more details? If there's codings, where things are numbers, but that corresponds to text values in a questionnaire, what were those codings? You might want to say what data type, or even give some descriptives about each column. What's the minimum value that could possibly go in there, the maximum value? And also data units. We'd be surprised how often data units get totally lost. And if you work in the hormone area, it makes an enormous difference. And there's so many different ways of describing like estradiol in the blood that it's hard to infer from the actual numbers. And additionally, missing values. Although I would say, like, please, please, please never use 999 to mean missing. If you ever see a paper that's got a really unusually large standard deviation for age, it's often because somebody used 999 to mean missing and nobody caught it and just like put it in there with the average and the standard deviation. But if you're using other people's data, you need to report what it is they did, and if what they did was bonkers, you should make a note of it. All right, so I've said literate coding like 8 times so far. So what literate coding is, let's define it here. It's an approach to programming that focuses on the creation of a document containing a mix of human readable narrative text and machine readable computer code. So if you've ever created an R Markdown document or Quarto document, which is very similar to R Markdown, Python, like Jupyter notebooks, these are all ways of doing literate coding. You have bits like the 2 hashes here before data exclusions creates a subtitle, like a level 2 subtitle, and then you can put some text, narrative text that doesn't need to have comment lines before it. And then you can put your code inside of these code blocks. So here this is a Quarto or R Markdown, would be the same for either. Code block, you have 3 backticks and then curly brackets, you say what language the code is in. And then you can put comments inside of that, and you can also put code in there. This helps reviewers to break things down into kind of coherent chunks of here's a bunch of code that does one specific thing. And it also encourages you, I think, to explain things a bit better. If you have to put your explanations in as comments, people will often try to make those really short, not put as many comments in. But when you've got free text, you can write paragraphs, bullet point lists, you can make links to things, And then this can all render to an HTML file that somebody can read through the text explanations of things and then look at the code, and even have cool tools like code folding. So all of your code chunks fold up and you have to click on them to be able to see them, to make it easier for people who don't code to read through. I cannot espouse literate coding enough. It makes so many things easier. Another principle that can make your coding a lot better, make it easier for somebody to review, and something that you can recommend for people as a reviewer if you see them potentially running afoul of this, is single point of truth, or SPOT. So in this top code, we're simulating some data. We're going to simulate 10 participants who are in 2 different groups, and we're going to use our norm to sample from a random normal distribution, 10 values. So we've repeated 10 or 5, there's numbers that are dependent on each other. If I change my mind and want to have to simulate 20 participants, I need to change ID 1 to 20, group, the rep, and that 5 should be changed to a 10, and DV, the R norm, the 10 should be changed to a 20. So I'd have to get all of those, make all of those changes if I want to change one of them. And that makes your code harder to understand, how, say, the DV and the ID and the groups numbers correspond to each other, that they're all dependent on one thing. And it makes it a lot easier for you to accidentally make a mistake and those to get out of whack. In this particular example, I'm not sure what would happen specifically if they got out of whack, but like actually I think the DV would probably recycle. So the first 10 participants would get 10 DVs, and then the next 10 participants would have those exact same 10 DVs. It would sort of silently look like it succeeded while actually not doing what you expected it to do. So using single point of truth means setting parameter variables sort of at the top of a section of code where you're going to be using that a certain number or a certain value more than once. So we set n equals 10, and then we can just use n in all the places in the code that are relative to n. That's the only concept that we need to define, and if we want to change it, we just change line 1 to n equals 20, and everything else changes as well. A sort of similar coding concept is called don't repeat yourself, or the dry concept. So if you're doing something like subgroup analyses, here I've only got an example of 2 of them, so it doesn't sound like such a big deal, but that's just to fit it on the slide. But often, you'll find yourself, there's 6 different kind of subgroups, or you're looking at 3 different DVs with 2 different subgroups, so you're going to have 6 analyses, and you're just writing the same code over and over again. Doing some filtering, you make a plot, you do the analysis, you do some follow-up analyses, but it's always the same. It's just on a slightly different filtering of your data set. So here we've filtered our data frame to group A and did a t-test, and then we filtered it to group B and did a t-test. So what you can do is write a function, encapsulate all of the code that you need for the thing that you've been repeating over and over again inside of the function, give it arguments for the things that change about it. So here, we need to tell it what's our data frame, and what's the level, like what's the level of group that we want to filter down to. And then we can use those variables inside the code. And then each of our analyses, instead of all of the code that we had before, which granted was only 2 lines, now it's just a single line of analysis. A is just subtest on DF for level A, and analysis B is subtest on DF for level B. And you can see how this becomes more and more useful the more your code is repeated, or the longer the code is that's being repeated. The final kind of concept that I wanted to get across to people is this idea of unit tests. Now, unit tests check to see if something is true about your data, your analysis, something that you want to double check that, after I've reshaped these data or excluded these participants, there should be 240 rows in this data set, so that if later in the future you've done some more things to your data, added a bit of code to do something else, and what it's actually done by accident is filtered everybody out of your data set and there's nobody in there anymore, or filtered in instead of out, that it would catch this. Now you can write these sorts of things yourself. You can just write nrow sim data is equivalent to 240, and then check, is that true or false? But the test that package gives you some really nice tools for checking things. And also you can, if you start working with test that, you can build on that for package development if you ever decide to do that in the future. So the test that package gives you some functions like expect to equal. So here we've got the object of the number of rows in sim data. We're expecting that to be 240. If we check it, we run that, and if it's true, nothing happens. But in the second test, we're expecting an equivalence between two vectors. So vectors are like the C, cat, dog, ferret. An equivalence here just means they should have the same items. They're not necessarily going to be in the same order. So the species column in sim data is a factor. We want to check what levels it has. And if we expected it to have levels of cat and dog and ferret, but we get an error here. Turns out it's not equivalent to cat, dog, and ferret. There's actually only two things. It's just cat and dog. So it'll make your code create an error if things aren't as you expected them. And here errors are good. They've flagged to everybody, oops, something has gone wrong. This is not right. And then you'll need to write a little bit of explanatory text around your unit tests, explaining what is it you're testing in case somebody else runs the code. But these are ways more to make your particular code bulletproof, to kind of do code review for yourself, as opposed to giving it to somebody else or doing code review for other people. Unit tests are kind of a way to self-check, but do require a bit of experience about not just checking for trivial things that must be true and probably won't ever go wrong, but things that you think are likely to go wrong if you messed up at some point. All right, so as I would talk about the code review guide. So we've got a big project that I've neglected for the past month because I've been working on many phases things. But the code review guide, right now, there's a big outline. You can check on github.com/code-check-club for discussion board and links to all the various things that we were doing. We've got a brainstorming document, but there's also an outline for a guide that we've put together, and people have claimed different sections of the guide. So somebody's written a section on the dry, like don't repeat yourself, or single point of truth, or a section on literate coding. So I want to especially thank the people named on this slide because they've written a few of those sections that I cribbed from for this talk. But if you want to get involved, there's also every section, once it's been written, needs 2 reviewers to go through it. And ideally somebody who's got some experience with code review and somebody who has very little experience to say, does this make sense to me? So you can sign up to write sections or to review sections. It's all on a Google document, and absolutely anybody's welcome to get involved in the project, which I will sort of get back to quite soon. All right, and I just want to say, actually, I'm doing good for time. Thank you so much. That is the talk. This is the URL, so you can access all the talk slides and the code that I created to, or that I used to create the slides. They're all done in Quarto Reveal.js. And I wanted to remind people who are in the UK that the UCU is going to be on strike this week and next. Please support your local striking members. Join the UCU if you can. And thanks.
Brilliant. Thank you so much, Lisa. That was amazing and really useful tips there. So I'm just going to look at the Q&A message board. So we've got one comment saying that they love the dry concept. And we have another one who asks, can long processes of data analysis be shared on Zenodo, or there are other platforms that notifies the user about the long processes and just provides the output?
I'm not quite sure what you mean by shared on Zenodo. So you can share the code for a long process. But what I want to recommend is, in that bit where I talked about the have an overview script, one that runs all your scripts in the right order. Make it so that the code that is in charge of the very long process is sort of moved out of there or not evaluated in a normal run. So if somebody was just going to like click run on your script and try it, it would skip over the bit that takes 14 days or 2 hours or whatever. It'll have a note that says this process takes this amount of time, or these particular resources that you probably don't have, therefore is not being run, with a link to the code or the code there, but in a non-evaluated code chunk. And then underneath that non-evaluated code chunk, you can just load the processed object data, whatever the long running process created. You can just load that from file and continue on with the rest of the code. It's basically just thinking about if a person wants to review this, if there's a big barrier that they're going to run into, how do you help fix that?
Awesome, brilliant. I have a question, Lisa, and it's sorry if you covered this in the talk, but so there was one issue that was flagged up in a previous Rights Club, which was actually an introduction to Python. And one of the things that was flagged up is that one of the issues with reproducibility is trying to recreate the environment in which you run the code. So there may be a version issue on the package that you're using, and as soon as it gets updated, everything can go to mess. Do you want to just comment on that? Is there something equivalent in R that can sort of create their own environment that was there when you run the code and built the script?
Yep, no, that's one I should have added in here. There were two things I knew I needed to add, and unit test was one, and I couldn't remember the other. And this is encapsulated environments, or I'm always forgetting the word for this. But so there's one thing for R is the renv package, RENV. Maybe other people call it RENV. You never know with R packages. But this keeps a copy of the version of R you're using and the version of every package. This can be really useful, especially if you're using packages that aren't found on CRAN. Something I kind of forgot to talk about as well. That another major reason why code doesn't run is that it uses a package or external resources that it's not straightforward for the reviewer to get. Now, if you're working in R, packages are normally, you find them on CRAN or maybe Bioconductor. But if they're something that's in development and you had to get it from somebody's GitHub page, and the package itself is called demo package, I know for a fact that there's like at least 50 people who have a package called demo package that they're working on right now because they're doing coding club with me on Wednesdays. So a person's not going to be able to Google it and find it and figure out what to do. So you need to tell them, do not install packages. This is one of my bugbears. Don't install packages in the code in a script that you're going to give to somebody else, because I don't need to reinstall tidyverse. I don't need to install mbest, which takes like 10 minutes to install. I don't want your script to force my computer to download something. That's a violation. But if you like write the install code and comment it out, then I can see if you've used an unusual one, like something that requires an installation from GitHub, then I can see how to do that. But Rend will just keep a copy of all of that, so it's part of the R project. And when you download the R project, you also get all of the code for the packages. So if the packages change in the future, become inaccessible, it's still there. So that's really good. And there's things like Docker. Containerization, that's the word I was forgetting, where you can containerize your code, your operating system, absolutely everything, and you run all the code from inside the container. So ideally, you run it from the container, you can give it the container to somebody else, and they run it from in there, and everything that's needed to run the code is in there. And so you can put Docker things online. There's an R package for Docker. There's a name I can't remember right now. And there's also services like CodeOcean that will kind of do containerization for you. And there's more and more journals that are partnering with CodeOcean, so that, like, if you've got your analysis code and your data, they'll create a container for you, and those are accessible online. You can just go in and run somebody else's code from online. You can even, edit the R, and it doesn't save to their code, but you can open up your own R session online and go explore their code and their data.
Awesome. So there was a nice comment from Professor Neil Martin, and he goes, no question, but just wanted to say that it was a brilliant talk, a masterclass in exposition. Thanks, Lisa, and that's getting upvoted as we go along. So it was a nice thumbs up for you there. I have another question about the book point that you made, that code reviewers are not there to identify bugs, but rather just to see, if the code runs, and yes or no. Could you see a kind of component of the bug bounty sort of approach being incorporated within code review? So I guess the perspective I'm coming from is that it would be great to sort of incentivize reviewing code and making sure it is reproducible, and I think the bug bounties is one approach, because people can actually pay people to review their code. But is there another way that you can try to incentivize code review in that way? So whether it's saying, would you review this code for me? If you spot an error, flag it up, and then incentivize it in some way, pay them to sort out the bug, or to identify exactly why the script is not running.
Yeah, no, I think, well, there's things like, not sure if it's still going, but the Red Team Science. Mm-hmm. So a place where you could pay people to do code review for you if there's nobody on your team. And that was a big barrier that people mentioned in the survey that we put out, was there's nobody else on their team who codes. They're the only person. They don't know anybody to do code review for them. So you could pay somebody on Red Team. You could, if your university has research software engineers, so Glasgow has research software engineers, and I could pay them to do code review. And we're going to start encouraging people to put money in their grants to get some code review done. There is also, let's see, it's called Code Check. There we are. So codecheck.org.uk is an organization where you can get your code checked. You can submit projects to there. Now they're only going to do that very first step of, does it run? And basically you'll just get a report back from somebody saying it ran, or no, it did not run. Here were the error codes I got, but nothing beyond that. But potentially, like, creating more, having a sort of code check club in your own institution of people who are doing kind of thematically similar things. They understand the analyses and the coding language that each other are using, and trading papers with them. I think the bug bounty thing, the people who've done it, like Ruben Arslan, don't get very many people actually looking at them. So I'm not sure if that's a great way to get all this done. But yeah, just wanted to show you all the Code Check Club on GitHub. We've got brainstorming doc, draft paper. The guide is online, but it's only the outline form. So the draft paper is, let's make that bigger. So like, people have, Kaja has written this one, and Claire and I have reviewed it. So you can just go through and sort of claim sections about what's going on. So this one's in progress, so somebody will finish that eventually, but you can go read through kind of what we have so far and then make your contributions to the code review guide if you'd like.
Oh, that's awesome. And I didn't know that about the bug bounty thing. That's always nice to see the dream versus reality, I guess. We're just on time, so I won't keep you any longer, Lisa. That was an absolute brilliant. I've thoroughly enjoyed it. Thank you so much for you giving your time on that and giving really useful tips. For those who are still here or joined late, please check out the recording which will be uploaded to our YouTube channel, and look at the future rights talks as well. And obviously make sure you make the Q&A very interactive like you did today. So thanks so much for everybody who came, and thanks of course to Lisa. Lisa, I'm going to end the live stream, and then you can stay on the line and we can just quickly debrief. And so thanks again, and see you later, everybody. Okay.